Da, da, da. Hello, hi class. It is I, M. Aikman. Yep, we are here back for another statistics lecture. I am very sleep deprived, but also very excited. So I figured to give people some time to arrive, I might have to yap a little bit. Today we're talking about z-scores, and I'm kind of excited. This is a shorter lecture, which is good. I don't know. I think it's good. You see, I got some intense news today about like my other teaching job at my other university, and so I'm going to be pretty busy. So after the current scheduled lectures that I have on the schedule up on my Twitter profile, I will probably have to take a bit of a break until things stabilize with the work at my other university. So we're going to get through this lecture and then both of the lectures next week. And then after that, I think I'm going to be taking a bit of a break to just make sure that everything is under control and, there's no minor or major disasters in the meantime. So I'm sorry about that if you were looking forward to one of the lectures that will be happening sometime in the future, like t-tests or ANOVAs or that sort of thing. But we will get to them. I will do them. I'm gonna have to take a bit of a break before I do them because my workload this semester is higher than anticipated. Let's put it that way. All right. But yeah, z-scores are fun. We're finally getting into some of the stuff that gets relevant for testing hypotheses. These are still considered descriptive statistics, so they're still kind of describing data and summarizing data, but they can also be used to test hypotheses and check for, not relationships between variables, but test if an intervention has changed one thing significantly, or whatever you want to call it. So we're finally getting into the more utilitarian stats that you might see reported in the results section of a paper, not just as like a side note, but as something of actual note, which is pretty exciting, I would say. I'm also just a fan of z-scores. I can't explain it. The vibes of them are pretty cool. Is that weird? I don't know. I'm at the point where like I have favorite statistical tests and statistical tests that just spark joy for me, and I don't know how to feel about that. But you know what? I mean, part of my job is teaching statistics, and I end up calculating some statistics and stuff for fun, just kind of on the side. So, hey, why not? I might as well enjoy it, right? And maybe one day you will too, if you don't already. If you do already enjoy statistics, welcome. You are in good company here. Super glad to have you. Oh, all right. Let's see. I'm sorry if my voice gets a little scratchy, by the way. I was not prepared for this semester. I forgot to do global warm-ups, or vocal warm-ups before the semester started. And at the end of one of my classes yesterday, my voice really started to give out on me. And that hasn't happened yet today, but I can already kind of feel it happening. Fun fact, when you're an introvert and you don't talk to people much, and then you suddenly jump to talking an hour or 2 hours at a time at like a high volume with little interruption, it does a number on your voice. Who would have thought? Oh my gosh. Anyway, let's pop on over to the lectures. There we go. There we go, look at that. There's my beautiful Z-score lecture. Are you excited? I'm excited. Let's get rolling. Let's not delay. So, z-scores. Here we go. Let me just adjust my windows for a second. There we go. All right, so far, in the previous couple lectures, what we've talked about, we've covered measures of central tendency, so things like the mean, the median, and the mode. And we've also covered measures of spread. That's what we did last time. So how clustered together or spread apart scores or like numbers are in a group of numbers. So for example, is everybody scoring about the same on an exam, or do we have some people scoring really high and some people scoring really low, with most people in the middle, or are people just all over the place? These are both types of descriptive statistics, so they're just trying to summarize and describe data. They're not trying to really draw any conclusions from data. Now, I mentioned last time in last stream that the results of the poll that I gave y'all about what type of examples you'd like to see, in this, y'all mentioned that you were interested in a mix of anime and psychology examples. So today, we are starting with an anime example. If you're not familiar with the anime, that's okay. I will give you enough information. So today's question, we're going to try and figure out how we can compare two scores from different distributions. So we're not saying, like, how did you and your classmate do on this exam? Which one of you did better? No, we're talking about, like, say, you and somebody from a different class. Or in this particular case, in this example, if you watch Kaiju number 8, which I think aired last season, this character is Kikoru. She is sort of a secondary protagonist. She's you know, she's awesome. I definitely recommend it. And about towards the end of the first season, Kikoru, everybody starts in the 3rd division of the Kaiju extermination group, and she is transferred to the 1st division towards the end of the 2nd season. So we might ask ourselves, or we can ask ourselves with Z-scores, is she stronger relative to her peers in the 3rd division or the 1st division? Essentially, is she kicking more butt than her peers in the 1st or the 3rd division? So we're comparing her to the people around her. You can think of it kind of like, how does she rank compared to the other people in her division? Is she really at the top of the strength hierarchy, or is she more towards the middle or the bottom? That's kind of what we're talking about. So, which one does she look more impressive in, is the kind of question we're asking here. Just to give you some lore, if you're unfamiliar with Kaiju number 8, they have sort of a power scaling thing called Unleashed Combat Potential, or Unleashed Combat Power. I think it kind of varies depending on the translation you're using. They wear these special suits, and these special suits allow them to perform superhuman feats when they're fighting kaiju, and the higher their unleashed combat potential is, the more powerful they are in combat, for the most part. Of course, the protagonist has to be an exception, or else would this really be a shonen manga, but their unleashed combat potential is on a scale of 0 to 100, with 0 being the absolute lowest and 100% being the absolute highest. So we might say, based on her unleashed combat potential, is she stronger in the 3rd division, where she was when she first joined the Kaiju Exterminating Corps? I forget what they call it, sorry. Or is she stronger relative to the other people in her division when in the 1st division, where she ends up by the end of the 1st season? Technically, her unleashed combat power varies a lot over the series, and I think it starts at somewhere around 43%, but for the sake of convenience and sanity, we're just going to round it to a nice 50%. I'm sure at some point in canon it was at 50%, because she crosses that line. So disclaimer, the numbers that I'm going to use in these examples are totally made up, and they do not necessarily reflect canon numbers from Kaiju number 8. Sorry. It's just easier to explain the math this way, and frankly, I'm here to teach you about Z-scores. I'm not here to teach you about Kaiju number 8. I'm sorry, Kaiju number 8. It's a good show, it's a good manga, I recommend it, but the point here is Z-scores, not Kaiju. So, here's an example of when we might want to use Z-scores. Let's say that this is a distribution of the unleashed combat power in 2 different divisions. This distribution on the left is the unleashed combat power in the 3rd division, where Kikoru starts out. And they have an average of 40, so their unleashed combat power is an average of 40% across all of the soldiers in this division. Then we have the 1st division, where she transfers towards the end of the 1st season, and let's say their mean combat power is about 60%. So they have their average combat power, their mean combat power is 60%, some people are lower, some people are higher. But as you get further away from that average, the rarer it becomes. And remember, for this example, Kikoru is at 50%. So, in the 3rd division, Kikoru's power, that 50% combat power, is 10 points above the mean, or 10% above the mean. But in the 1st division, her power is 10 points below the mean. Her combat power has not changed, but the group that we're comparing her to has changed. So the same number, that same 50%, may make her look pretty powerful in one group, but not so powerful in another group because the people we're comparing her to have changed. If we want to compare Kikoru's strength across these divisions, or relative strength compared to her, the other people in her squad, we can interpret this as the average, we're going to interpret it as her strength relative to the division's average strength. So we're not just saying how strong is she overall on the scale of 0 to 100. We're saying how strong is she compared to the other people in her division. That's the whole idea here. Now let's look at a different example. Let's say that in this case, this tall distribution here is the third division, and its mean is 40. So everybody in the third division, their average combat power is 40%, and that's pretty consistent. Most of them are pretty close to 40%. Most people are, say, between 20, 25, and 50 or 55. They're all pretty much at the same level of combat. They're pretty darn similar. But let's say the first division also has a mean of 40, so it has the same average combat power, but the variability is much higher. The standard deviation is much higher. Oops, sorry. That's why we see it wider. Yeah, the average is still 40. It has the same average as the third division, but it has some people that are way stronger than the people in the third division, and some people that are way weaker than the people in the third division. In the third division, where we have a very small amount of variance, Hikaru is stronger than 98% of her peers. In the first division, though, where we have a much bigger standard deviation, so let's say the standard deviation in the first division is only 5%, but in the third division is 5%, but in the first division is 20%. Because the standard deviation becomes bigger, there's a lot more variability in strength in the first division. In that case, Hikaru is only stronger than 69% of her peers. Sorry, typo there. So in this case, changing the standard deviation changes how good or how strong Hikaru looks, right? We are not only evaluating whether she's above or below average for her division, we're also evaluating this in terms of how much variability there is in the division's power levels. We want to know how much or how little, or like how much above or below average she is. And we can do that by taking variability into account. Yeah, there's your standard deviations again. Sorry for that. So the raw score, that 50%, doesn't provide us much information. So different anime use different sort of like power scalings. Initially, I wanted to compare like two characters in two different anime with different ways of power scaling. Like, for example, maybe compare Hikaru to Goku from Dragon Ball Z or Yo from Shaman King. Those also have their own, numeric power level systems. And you could do that with Z-scores, but unfortunately, it didn't work well in a graph because their scales are so different. But when I say Hikaru has 50% unleashed combat power, that doesn't necessarily tell you how strong she is, because in some anime, a lot of people are really at the top of the scale, and the average combat power across the entire anime might be 80%. So a score of 50% isn't that impressive. Or let's say you're looking at another anime where most people's combat power is like 10 or 20%. That's the average on this scale. And in that case, Hikaru's 50% sounds pretty impressive, right? So that 50% on its own doesn't tell us much. It just tells us she has 50% unleashed combat potential, but depending on who you're comparing that to, that might be really impressive, or that might mean that she's really weak. The thing that we're going to do here, and the thing that Z-scores are going to do, is they're saying, okay, we're not just going to tell you her combat potential is 50%. We're going to tell you if that's impressive. We're going to tell you if she's above or below average combat power, and how far above or below average she is. We do this by taking into account her distance from the mean, so her distance from average combat power, say 10 points above or 10 points below, and the variability of the distribution. How much variability is there in combat power? If everybody is exactly at 40%, that 50% becomes really impressive. If people are spread out all the way between 0 and 100, maybe 50% isn't all that impressive. So we're going to take both these things into account to try and describe how strong she is. And that's what a Z-score is. It's using whether you're above or below the mean, and then how far away from the mean you are, to try and describe how typical or atypical your score is, which can mean like, are you extremely strong or extremely weak or just average? Or it could mean, you know, like, are your symptoms extremely severe or extremely light, or are they average? It can basically, are you extremely high, extremely low, or about average on any given measure? That's what z-scores allow us to do. So yeah, z-scores, also known as standardized scores. Z-scores are these magical things, and here's the formula for them. Some notation notes. X of I is the score you're interested in, the score of a single person in your sample. So in this case, for our example, that would be Kikoru. Kikoru's score would go here. M is the mean of your sample. So let's say the average combat power is 40%. That would go here. And this allows us, this top part, the numerator, allows us to see how high above, or how far above or far below the mean our person is, in this case, Kikoru. The bottom here is the standard deviation of our sample, and this allows us to say how far above or how far below the mean your person is. So this is just saying, are you above or below? And this is helping us figure out how far above or how far below you are. Essentially, what the number that it spits out, your z value is what we call it, tells us how far away you are from the mean in standard deviations. It's essentially like, imagine you're using a ruler to measure distance. It's like that. Your standard deviation is the equivalent of like an inch. It's saying you are, if you're 3 standard deviations above the mean, that's the equivalent of saying like you're 3 feet away from the wall or something like that. We're measuring distance. How far above or below the mean are you, or how far away are you from the mean in either direction? That's what a z-score tells us. So let's practice calculating some z-scores. So here on the left, we have our third division distribution. On the right, we have our first division distribution. I've given you the formula for z-score up here. The mean for the third division is 40%. The mean for the first division is 60%. And the standard deviation for both in this example is 10. So let's see how far above or below the mean Kikoru is in the first and the third division. Let's calculate her z-scores. So first things first, let's look at the formula. And the first thing I always ask myself if I'm not sure where to start is, well, what information do I have? I've already told you that Kikoru's unleashed combat power, at least for this, example, is 50%. So her score is 50. So we know that this score is going to be 50. So I can start by plugging that in. Then to figure out if she's above or below the mean, we subtract the mean from 50. And right now we're working in the third division. I tell you down here, the mean of the third division is 40%. So that's 50 minus 40. Then, to figure out how far above or below the mean she is, we divide by the standard deviation. We look down here. I tell you the standard deviation for the third division's combat power is 10. So we put that down here. And now let's solve this equation. 50 minus 40 is 10. And then we divide 10 by 10. We get a z-score of positive 1. Now let's calculate her z-score for the first division. Her score is still 50. She still has the same unleashed combat potential, but now we're comparing her to the first division, where the mean is 60. So instead of subtracting 40, we're using the new mean. We're going to use that mean of 60. And then the standard deviation of the first division's combat power is still 10. So we're still dividing by 10. 50 minus 60 is negative 10. Divided by 10, Hikaru's z-score in the first division is negative 1. There you go. Simple as that. Calculating z-scores, as long as you have this information, is pretty easy. It's literally, you just subtract a thing and then divide. And of course, you can use your calculator for this. So if my handwriting is not fun to read, I've animated this out, what I just did. There you go. What this means for the third division, this z-score of positive 1, that means that Kikoru's combat power is 1 standard deviation above the mean in the third division. So she's fairly strong in the third division. She's above average, and she's 1 full unit of distance above average. In the first division, though, Hikaru's strength was a z-score of negative 1. This means that she's one standard deviation below the mean, and this means she's below average, and she's 1 unit of distance below average. So she's fairly below average in the first division. She still has exactly the same unleashed combat potential, but because we're comparing her to the other people in the division, we can see that she's stronger in the third division relative to her peers than she is in the first division. So she might get, like, put at the front of combat if she's in the third division, because she's stronger there relative to the other people, but she might be put more on the back lines and she's in the first division because she's weaker compared to the other people there. So yeah, there's your conclusion. By comparing these z-scores, we can tell that Kikoru was stronger in the third division, or relative to, her peers. Let's try another example. So here is our example 2. And this is where we change the standard deviation. So in this case, the mean combat power in the third and first division is both 40, so we're keeping the mean the same, but we're changing the standard deviation. The standard deviation for the third division is 10, and for the first division is 20. And we're still keeping Kikoru's score at 50. So we do exactly the same thing as we did before. We start plugging these numbers in. Hikaru's unleashed combat power is 50, minus the mean of the third division is 40, so she's 10 points above the mean, divided by the standard deviation of the third division, which is 10 in this case. And this is actually the same calculation we did on the last slide, so you probably already know the answer. 50 minus 40 is 10, divided by 10. This gives us a z-score of +1. Her combat power is 1 standard deviation above the mean. So she's stronger than a fair number of, the other people in that division. Now let's look at the first division. Her score is still 50. For this example, the mean combat power in the first division is 40. So we subtract 40. And in this example, the standard deviation in the first division is 20. So we gave a lot more variability to the levels of strength in the first division now. 50 minus 40 is 10. So she's still above average. In this example, she's above average strength. And then we divide that by 20. 10 divided by 20 is 0.5. She is half a standard deviation above the mean. And then on the next slide, just in case my handwriting, you don't like it, I animated this out. Oh, 50 minus 40 divided by 5. I had the wrong I'm sorry, I made a mistake. This standard deviation on this slide is supposed to be 5, not 10. For the sake of the example. So I'm going to redo the math real fast. My mistake. We made the standard deviation smaller, so everybody is roughly the same. But the math is still the same. The math is still pretty similar. You just do 50 minus 40 divided by the standard deviation of 5. 10 divided by 5 gives us a z-score of +2. She's 2 standard deviations above the mean. There we go. I'll fix that before I upload the slides. So there we go. So she's 2 standard deviations above the mean in the third division in this case. That means, yeah, she's 10 points above the mean, but because everybody is close to the mean, everybody in the third division is roughly around 40, give or take a few percentages. That's pretty impressive. She's stronger than most of the other people in her division. But in the first division, because it has such a big standard deviation, because there's so much variability in strength in the first division, she's only half a standard deviation above the mean. So she's still fairly average. She's above average, but she's still pretty close to the average combat power in that division. That's why we have to really care about variability here. The variability tells us, wow, is she really outstanding? Or is she about average? And if you just looked at her score compared to the mean, you'd think that she was about the same level of strength in both relative to her peers, but no. Because there's so much more variability in the first division than the third division, she stands out way more in the third division than the first division. Because I think I said that wrong. Because there is more variability in the first division than the third, she looks more impressive in the third than the first. Wow. graph, you can see there's a lot more people to the right of her in the first division where there's a lot more variability. Very few people to the right of her, higher than her in the third division where there's little variability, even though in both cases she's 10% above the mean. That's what I'm saying. All right. So in this case, relative to the rest of the soldiers in her division, she stood out more and she seemed stronger in the third division than in the first division. Not because, she was 10 points above in both. The amount she was above the mean was the same in both, but because the variability is different, that means she's a lot stronger than most of the third division with that 10-point difference, but that 10-point difference only makes her a little above average in the first division. That's why we take variability into account. Now, z-scores, these lovely scores that allow us to figure out how far above or below the mean somebody is, have three properties. And that first property is that the mean of a set of z-scores is always 0. If you add up all the z-scores for any given data set, they'll all add up to 0. Why? Well, let me tell ya. First things first, the mean's the balancing point of the set of scores, and the sum of all standard deviation scores add up to 0. What this means is that essentially half of people are going to be above the mean, half of people are going to be below the mean because of how the mean is calculated. If you add it all up, you'll get something. You'll get the mean. And I think I can also explain this through the formula. The formula for a z-score is a score minus the mean over the standard deviation. If I plug the mean in as my score, you end up with the mean minus the mean over the standard deviation, which equals the mean minus itself is going to be 0 over the standard deviation. If you plug the mean into a z-score formula, you're always going to get 0, because you're subtracting the mean from itself. Remember, z-scores are a measure of distance. How far are you away from the mean? If you're at the mean, you're at the mean. If you're at the mean, you are 0 distance away from the mean. So the mean of a set of z-scores is 0, because that's how far away you are from the mean on average. If you're the mean, you're 0 away from the mean. You are at exactly the mean. The mean of a set of z-scores will always be 0 for all of these reasons. The second property is that the standard deviation of a set of z-scores is always going to be exactly 1. Why? Well, this is because z-scores, well, first off, mathematically speaking, let's look at that formula again. The formula for z-scores, again, is a score minus the mean over the standard deviation. Let's say our score is exactly 1 standard deviation above the mean. So let's say the mean is 50, the standard deviation is 10, and if your score is 1 standard deviation above the mean, that means it is 10 points above the mean, if the standard deviation is 10. So 50 plus 10 equals 60. 60 is exactly 10 points above the mean. It's 1 standard deviation above the mean. So if we plug that in, 60 minus 50 over our standard deviation of 10, you get those standard deviation back, and you end up getting 1. So mathematically, that's why the standard deviation is 1. Theoretically, why it's 1 is, remember, z-scores are a measurement in units of standard deviation. The base unit, like the inch or the pound or the centimeter, whatever you want to call the base unit, that is 1 standard deviation. If your z-score is 1, that means you're 1 standard deviation above the mean. A z of 1 is exactly 1 unit, and the unit is a standard deviation. That is why the standard deviation of a set of z-scores is always 1, because 1 z is 1 standard deviation, and therefore is 1. And again, mathematically, if you're 1 standard deviation above the mean and you plug that into the formula, you will end up getting the result 1, because you end up dividing the standard deviation by itself. Whew. Oh, I need to erase this. So I earlier referred to z-scores as standardized scores. Z-scoring is one way to standardize scores. And what this means is no matter what scale I start on, so maybe I'm using Kaiju number 8's Unleashed Combat Power on a scale of 0 to 100, or I'm using Dragon Ball Z power levels that go up into the hundreds of millions, or I'm using Shaman King's, I forget the name of the power, but I'm using Shaman King's measure of mana, and that goes into I think the tens of thousands or something like that. Or if I'm using a scale of 1 to 5, or if I'm using Jujutsu Kaisen's, grade 3, grade 2, grade 1 sorcerer, special grade, whatever, no matter what scale I start on, if I Z-score it, it will always turn it into having exactly the same mean and standard deviation. So no matter what scale you start on, once you Z-score it, you can compare those numbers directly to each other to see which one is higher and which one is lower, which is why I wanted to, say, compare Kaiju number 8's power scale to, Kill la Kill's power scale or Dragon Ball Z's power scale, but unfortunately that didn't end up working out. But if I had more information on those other power scales, I could have done that. I could have directly said, in their own universes, who is stronger, Goku or Kafka from Kaiju number 8. I could have said, relative to the other people in their universe, who is stronger. I could have done that. I could do proper power scaling relative to, the levels of power in their world if I had enough information to calculate the Z-scores for these power scales. Because Z-scores turn everything into exactly the same scale. Mean of 0, standard deviation of 1. Please don't Z-score in power scaling debates. Power scaling debates are as much of a headache, they're already a headache. But you know what? You could do it. If you wanted to, you could do it. And it takes away a lot of the problems that come along with, comparing things on two completely different ways of measuring power. All right, the third property of Z-scores. If you have a distribution of a set of scores, and you Z-score it, the distribution shape will not change. So I know it's been a minute since we talked about the shapes of frequency distributions, but let's say I have something like this where this is kind of lopsided, but the mean power level in a division is 40%. About half of people are above that, half of people are below that. Or let's say I have something like this, which is, I think, based on what I remember from Kaiju number 8, their power scale is actually more like this. You have most people whose power, I think the average was 14% or something for new recruits. And then you have very, very, very few people who are 90% plus. So Kaiju number 8's power scale is a positively skewed distribution. If I Z-score these percentages into Z-scores, it will not change the shape of the distribution. So if I have a skewed distribution like this for Kaiju number 8, Z-scoring it is not going to turn it normal. This is not a thing that works. It does not change the shape of the distribution. Z-scoring does not change how the things are distributed. It stays the same. The only thing that it changes is the numbers on the x-axis of your graph. So here is not Z-scored. It looks like this is on a scale of 0 to 1. Here's at Z-scored. You can see the shape of the distribution is exactly the same. The only thing that's changed is this is on a scale of 0 to 1, and this one has the mean at 0 and then goes out from that in either direction. So now that we've established that, I am going to do a quick little comprehension check. You do not have to participate if you do not want to. That is totally fine. But if you are watching this VOD, I would like you to look at these 3 graphs and ask yourself, which one of these graphs represents a set of Z-scores? I'm going to give you a minute. Is it A, B, or C? Which one of these distributions is a distribution of Z-scores? The answer is C. C is our distribution of Z-scores. How can you tell? Well, first rule of Z-scores, the mean is always equal to 0 of a set of Z-scores. And this is a normal distribution. We talked about this last week. A normal distribution is unimodal, so there's only one mode, there's only one high point, and it's symmetrical. And all 3 of these are unimodal and symmetrical. All 3 of these are normal distributions. What that means is that the mean of these distributions is right at the middle. the mean of the distribution A is 4. And if all sets of z-scores have a mean of 0, it can't possibly be A. The mean of distribution 3, the number right in the middle, is 2. And again, if all sets of z-scores have a mean of 0, this doesn't work. C is the distribution that has a mean of 0, so this is the only one that could possibly be a distribution of z-scores. So, to summarize all that, the 3 properties, here's a slide with all 3. The 3 properties of z-scores, their mean is always 0, the standard deviation will always be 1, and standardizing scores into z-scores does not change the shape of the distribution, it stays the same. Now, let's say you've got z-scores, and that's awesome, but you want to convert them back into their original units. You want to convert them back into percent of, or like combat power, unleashed combat power, or you want to convert them back into inches, or you want to convert them back into score on some sort of depression scale, or something along those lines. It's pretty easy to do. All you have to do is you take the z-score equation and you solve it for x. That is literally what I've done here, where x, again, is the raw score. Z is your z-score. SD is the standard deviation of the original distribution. And M is the mean of the raw distribution. So our old formula for calculating a z-score from a raw score was z is equal to a score minus the mean over the standard deviation. We get this formula to convert a z-score back into a raw score by just solving this for x. First, we multiply both sides by the standard deviation. And that gets rid of that. So that's the standard deviation times z is equal to x minus m. Add m to both sides, add the mean to both sides. That cancels out. And we end up with the standard deviation times z plus the mean equals the score. So that's how you can convert back and forth. I am sorry that these two things reversed in how I was doing that, but really it doesn't, multiplication doesn't care about order, so. So let's try an example here. Let's say somebody's mean combat, or we're converting we know that somebody has like, their unleashed combat score is two standard deviations above the mean. Their z-score is 2. And we want to find out what their actual combat, like unleashed combat potential is. We want to find out what that is. We know it's 2 standard deviations above the mean, so they're very strong compared to whoever they're being compared to, but we want to know exactly how strong. So let's start plugging this in. To solve this, we do the score that we're looking for is equal to our z-score, 2, times the standard deviation from the original distribution, 7, plus the mean of the original distribution, 69. We're gonna, I think, let's see. Let's subtract 69 from both sides. Or wait, no, what am I doing? That's the wrong way to solve this. I got stuck on the old solving for x, and that's not at all what we're doing here. The first thing that we do, let's multiply 2 by 7. Remember order of operations, PEMDAS. So 2 times 7 gives us 14. Plus 69. And then we add that, 14 and 69. So that is 79, 83. I did that math in my head, so let's find out if that's correct. I have this animated here. So we have that z-score of positive 2 times the standard deviation of 7 plus the mean of 69 is equal to 14 plus 69 is equal to 83. Yeah. So this person, in this distribution, where the mean is 69 and the standard deviation is 7, somebody who's 2 standard deviations above the mean has an unleashed combat potential of 83%. So they're pretty darn strong based on Kaiju number 8's rules. I think the cutoff for like being an officer is around 80%. So they're pretty darn cool. So z-scores are great because they allow you to standardize scores. You can compare across all different types of scales. If I wanted to compare Goku's power levels to, say, the skill of the protagonist of Welcome to the Ballroom. I wanted to see how proficient who was the most proficient at their respective field, fighting and ballroom dancing. I could convert those into z-scores and compare directly who is the most overpowered protagonist. I could do that. I don't know why I'd want to, but like if I wanted to, I absolutely could do that. Now, because we have this, we can interpret Kikoru's relative strength in two different divisions on the same metric. Even though we're comparing her to two different groups, we can say, oh, she's stronger in this group than she is in that group. We're not just relying on the fact that she's at 50% combat power, we're comparing her to the rest of her group. In example 1, we can say she got a z-score of +1 in the 3rd division and a z-score of -1 in the 1st division. She's above average in the 3rd division, but she's below average in the 1st division. But of course, not everything is good. Z-scores have disadvantages as well. For one, because you are comparing a person to some sort of reference group, the average other person in the squad, if you change the reference group, that person's z-score might change. So let's say I'm still in the 3rd division. I'm comparing her to the 3rd division. But let's say the old recruits in the 3rd division are weaker and the new recruits in the 3rd division are stronger. If I change the people that I'm comparing her to, her z-score might change even though we're still comparing her within the same division, and that can get a little confusing. The second disadvantage is that when you z-score things that have actual meaning, that meaning can get lost. So let's say, for one example, let's say you want to ride a ride at an amusement park. And you know, often when you're standing in a line, there will be a sign that say, you must be this tall to ride. If the attendant says, hey, are you at least, say, 5 feet tall? You need to be 5 feet tall to ride this roller coaster. And you say, oh, well, my z-score for height is -0.5. Do they actually have the information that they need? Absolutely not. They have no idea what a z-score of 0.5 means. First of all, not a lot of people know what a z-score is. Second, that you can't even convert that back into the original score if you don't know what group you're comparing them to. Am I a z-score of -0.5 in, say, height based on compared to people in North America, or compared to people in East Asia, or compared to people in Scandinavia? What is my reference group? Even if this person knows what z-scores are and knows my z-score and the mean and standard deviation of the reference group, they still, well, if they don't know the reference group, if they don't know the reference group, they won't be able to calculate how tall I am. That just, at that point, telling them the z-score is kind of useless. In this case, let's say, if Kikoru says, oh, well, my z-score in combat potential is +2. I mean, that sounds impressive, but we don't know who she's being compared to. If she's being compared to just civilians, yeah, of course she's much stronger. If she's being compared to the other people in her division, that's probably more impressive. Also, let's say a mission, you need a combat power of at least like 30% for you to have a good chance of surviving this mission. If she says her z-score, that doesn't tell you if she's above or below the threshold for going on this mission. That doesn't tell you anything useful. The z-scores are really handy, but like if the original score has some sort of meaning, it's lost when you convert it to a z-score. So let's sum all this up. Z-scores are great because they put all the scores on the same scale, no matter what scale they started on. They tell us how far and in what direction a score is from the mean. A z-score is positive if you're above the mean and negative if you're below the mean. And the further you are from 0, the further you are from the mean. So a z-score of +5 means you're way above the mean. A z-score of -1 means you're a little below the mean. The mean of a set of z-scores is always 0, and the standard deviations of a set of z-scores is always 1. That's z-scores. I'm happy to answer any questions that you may have. I'll sit for a bit. I think I'll count to 10. I don't know if anyone's currently watching, but just in case. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10 Mississippi. I know there's lag between when I say something and when y'all hear it, so I wanna make sure that I'm not missing any questions. But of course, if you do have any questions, feel free to drop them into the comments section and I will get to them as soon as I can. I think that is it. So I hope that you all have an absolutely wonderful day. Take care of yourselves and I will see you next class. Bye everyone. Bye bye.